Civilization was built not with bricks, but with ideas. We are about to trace the epic journey of abstract engineering, from the first controlled flame to the complex formulas that power our world today. By the end of this story, you will see the entire modern landscape as a physical manifestation of human thought. How did ancient builders erect monuments like the Great Pyramid without modern math? What cognitive leap allowed us to design machines for environments we could not even visit? This is the history of how we learn to turn imagination into reality. What does it truly mean to engineer a dream? That first controlled flame was more than just a source of heat. It was humanity's original act of engineering. Deep within South Africa's Wonderwerk Cave, scientists found the earliest evidence of this momentous shift, remnants of ash and burned bone dating back over 1 million years. This was not a random wildfire. It was a managed, contained process. To keep a fire going required foresight, a plan for gathering fuel and tending the embers. This was the first abstract leap, the conscious control of a powerful natural phenomenon to achieve a predetermined outcome. Think about the immense conceptual jump here. It was not about merely using a burning branch from a forest fire, but about deciding to create and maintain that fire for specific purposes, for warmth against the cold, for light in the darkness, for protection from predators. This act of taming a chaotic element planted the very seeds of engineering thought. It proved that nature's rules could not only be observed but actively harnessed. From this primordial spark, everything else would eventually ignite. The deliberate heat of that fire would later bake clay into durable pottery and smelt rocks into gleaming metal. But first, we had to learn to command the flame itself, the foundational skill that taught us we could reshape our world. That single flame eventually transformed the entire landscape. As humanity learned to cultivate the land, we stopped simply reacting to the world and started actively redesigning it. This was the Neolithic Revolution, a profound shift from a life of nomadic instinct to one of settled intention. With agriculture came a new set of abstract challenges that required foresight and planning on a scale never before attempted. Communities now had to design systems for a future they intended to create. The simple plow was one of the first great engineering solutions to this new way of life. It was not just a shaped piece of wood, it was a tool conceived from the abstract idea of turning the soil to increase future yield. It turned the chaotic earth into orderly rows, a physical manifestation of the concept of planned cultivation. This same forward-thinking logic applied to water. Early farmers could not rely on rain alone, so they engineered the first irrigation channels. These were not just ditches, they were a deliberate network, a designed system to move water from a river to distant fields based on a shared understanding of gravity and flow. Can you envision the mental model required? The ability to see a map of watercourses in your mind before a single shovel of earth was moved. This cognitive leap is stunningly visible in places like Çatalhöyük, one of the world's first known cities. Here, thousands of people lived in a dense, interconnected settlement without any written language, streets, or central authority. How did they build it? They operated from a shared, abstract blueprint for community life. Houses were constructed wall to wall, with entry through holes in the roof. This was not random. It was a collectively understood design for security, social structure, and shared living. The entire city was a physical expression of a complex idea, engineered and built through non-verbal consensus. Perhaps the ultimate symbol of this new engineering mindset was the granary. Before agriculture, you ate what you found. Now, with surplus, you had to think about next season, next year. Building a structure to protect your harvest from pests and weather was an act of faith in the future. It was architecture dedicated not to immediate shelter, but to the abstract concept of food security. This required understanding ventilation to prevent rot and structural strength to support the weight of grain. Every decision was a calculation for a tomorrow that had not yet arrived. This was the true turning point, the moment we began to engineer our world not just out of immediate need, but from a vision of what could be. But the abstract engineering of the farmer's granary was only the beginning. The same foresight that planned for the next harvest soon turned its gaze toward the heavens. Rising from the plains and plateaus are monuments that still defy easy explanation, structures like Stonehenge and the Great Pyramid. These were not built with formal mathematics as we know it, but through a profound, hands-on understanding of geometry and celestial motion. Their creators possessed an abstract genius, an ability to encode the cycles of the sun, moon, and stars into colossal stone. The Great Pyramid is a perfect example. Its base is almost a perfect square, with sides aligned to the 4 cardinal directions with an accuracy of a fraction of a single degree. How could ancient builders achieve such precision without modern tools? They were masters of applied geometry, using simple ropes and stakes to physically manifest abstract relationships of circles, lines, and right angles on a truly gigantic scale. The pyramid's very shape, its steep, smooth sides, represents an understanding of pi, the ratio of a circle's circumference to its diameter. It is as if they built a mathematical constant into a mountain of stone. This was not merely architecture, it was a physical formula. The same abstract reasoning is etched into the Salisbury Plain. Stonehenge's ring of towering sarsen stones functions as a sophisticated astronomical calendar. Its heel stone marks the precise spot where the sun rises on the summer solstice, and other alignments track the complex motions of the moon. The builders were not just stacking rocks, they were building a permanent model of the cosmos itself, a computer made of stone that could predict celestial events for generations to come. The engineering required to execute these visions was as abstract as the astronomy. How do you move a stone weighing 50 tons across dozens of miles? How do you lift it and set it perfectly upright? This required more than muscle. It demanded a sophisticated logistical model held entirely in the mind. They had to conceptualize leverage, friction, and mass distribution long before any load was moved. They engineered ramps, sledges, and counterweight systems, turning abstract principles of physics into tangible reality. These structures were the ultimate expression of a new kind of thought, where the human mind began to engineer not just for survival, but to capture the eternal rhythms of the universe in a language of stone. The stone monuments were a testament to a mind that could hold the cosmos within it, yet that knowledge remained locked in the minds of master builders and their apprentices. Then came a development as monumental as the pyramids themselves, the invention of writing. In the fertile river valleys of Mesopotamia and Egypt, humanity learned to trap speech in clay and stone. This was the moment abstract engineering found its voice. For the first time, a complex idea was no longer a fleeting thought, but a permanent, tangible object. Cuneiform tablets from ancient Sumer are not just historical curiosities, they are the world's first technical manuals. One tablet might detail the exact dimensions for a temple foundation, while another lists the materials and labor required for a city wall. These were not poetic stories or royal decrees, they were precise, actionable instructions. Can you grasp the sheer power of that shift? An architect's design could now travel across space and time without the architect being present. A master builder's knowledge did not die with him. It was etched into clay, waiting to be read and understood by a future generation. This was the birth of cumulative knowledge. Engineering was no longer a craft passed down through fragile oral tradition, where a forgotten detail or a misremembered number could lead to catastrophic failure. Now knowledge could be stored, verified, and systematically improved upon. A crucial part of this new language of construction was the development of standardized units. The cubit in Egypt, for example, was not just any length of an arm, it was a fixed, agreed-upon measurement. This was an abstract concept made real, a shared understanding of size and quantity that allowed a team of thousands to work in perfect harmony. One person could carve a block of stone in a quarry miles away, confident that it would fit perfectly into a slot prepared by another worker at the construction site. This common language of measurement was the invisible framework upon which every great structure was built. Writing did not merely record what engineers did, it fundamentally transformed how they thought. It forced a new level of precision and planning. You could not write down vague instructions for mixing mortar or aligning a wall. You had to specify exact proportions and angles. This process of codification turned intuitive craft into a verifiable discipline. The abstract principles of geometry and physics, once understood only through practice, could now be articulated, debated, and refined. The stage was now set for the next great leap, where these written descriptions would evolve into something even more powerful, the predictive formula. The written word gave engineering a memory, but metal gave it strength and purpose. Deep within a Bronze Age forge, a transformation was taking place that redefined reality itself. Artisans were no longer just shaping the materials they found, like stone or native copper. They were beginning to create entirely new substances from scratch. This was the miracle of bronze, an alloy born from the marriage of soft copper and the rare, brittle metal known as tin. The process was not a simple one. It was humanity's first deep dive into material science, a long and painstaking trial and error process conducted in the searing heat of the furnace. These early metallurgists had to discover the perfect smelting temperature, a point hot enough to liquefy the metals for mixing, but not so hot as to spoil the batch or waste precious fuel. They had to determine the ideal ratio, typically around 9 parts copper to 1 part tin, to produce a metal that was harder than copper, held a sharper edge, and was less brittle than tin alone. This was not a physical task so much as a theoretical one. It required the smith to conceptualize the internal, invisible structure of the metals and to predict the outcome of their combination long before the crucible was ever poured. Can you envision the mental leap to believe that two ordinary things could be merged to create a third, superior thing with properties that did not exist in nature? This was abstract engineering in its purest form, a recipe held in the mind that turned raw elements into a world-changing tool. The creation of bronze also points to a vast, unseen network of abstract thought. Tin is a rare ore seldom found near sources of copper. To obtain it, societies established trade routes spanning thousands of miles, from the mines of Cornwall in Britain to the workshops of the Eastern Mediterranean. This required a sophisticated system of logistics and economic planning, a shared understanding of value, measurement, and future demand that connected distant cultures who might never meet. The bronze that tipped a spear in Mesopotamia was the product of a globalized supply chain, a concept we think of as modern, yet it was fully operational over 3,000 years ago. In that fiery crucible, humanity was not just mixing metals, it was mixing matter and mind, proving that through abstract thought and deliberate process, we could reach into the very building blocks of the world and engineer a better one. While the bronze smith relied on intuition and observation, The Greek mind sought to uncover the hidden logic behind the lever and the pulley. In the city of Syracuse, a single thinker would transform engineering forever by demanding proof. Archimedes did not just use tools, he dissected their very principles with the razor of geometry. His legendary declaration was not a boast about strength, but a profound insight into the power of mathematics. "Give me a lever and a place to stand, and I shall move the world." This statement reveals a complete faith in an abstract relationship. He understood that the physical world operates on rules that can be captured and manipulated through numbers and ratios. The lever was not a mere wooden beam, it was a physical expression of a mathematical law. The longer the arm on your side, the less force you need to lift a heavier weight on the other. Archimedes did not simply observe this, he proved it. Using the precise language of geometry, he demonstrated why this relationship must be true, establishing a fundamental formula for mechanical advantage. This was the critical shift. Engineering was no longer just about what worked. It was about knowing precisely why it worked and being able to calculate the outcome before a single piece of wood was cut. His genius extended to the water's edge. The story of him leaping from his bath and running through the streets shouting "Eureka" is a celebration of abstract discovery. He was tasked with determining if a king's crown was pure gold without damaging it. The solution did not come from examining the crown itself, but from a sudden understanding of displacement. He realized that an object submerged in water displaces a volume of liquid equal to its own volume. By comparing this volume to the object's weight, he could deduce its density and therefore its purity. This principle of buoyancy was another universal law, written not in stone but in the behavior of matter, and he had found its mathematical key. Archimedes used this same geometric rigor to calculate areas and volumes with astonishing accuracy, devising a method to approximate the value of pi. He was effectively creating a toolkit of proven, reliable calculations that an engineer could use to design a ship, a pump, or a siege engine with confidence. The physical craft of building was now married to the abstract science of prediction. This union meant that a machine could be designed on papyrus, its strength and function verified by mathematics, long before it was ever built in the real world. The age of trial and error was giving way to the age of the blueprint, a plan drawn not just from experience but from proven, unshakable truth. Archimedes had proven the power of the lever, but could that same abstract principle of calculation be stretched across an entire continent? The Roman answer was carved into the landscape itself, in the form of aqueducts that marched over hills and through valleys. This was engineering at an imperial scale, a breathtaking application of a simple hydraulic idea to the problem of sustaining millions. The core concept was almost childlike in its simplicity: water flows downhill. Yet to execute this idea over 60 miles of wildly varied terrain required a level of sustained abstract planning never before seen. Roman engineers had to hold a perfect, continuous downhill slope in their minds for the entire length of the aqueduct, a gradient so slight it dropped only a few feet every mile. Maintaining this invisible line was their supreme challenge, a feat of geometric foresight that made the pyramids look like a single, static calculation. Their most crucial tool for this was the chorobates, a 20-foot-long wooden frame with water-filled channels and plumb lines. This instrument was not for moving earth, but for seeing an abstract truth. It allowed the engineer to visualize a perfectly level plane across the rough ground. With it, they could precisely determine how much to raise or lower the aqueduct's channel at any point to keep the water flowing at that perfect, gentle pace. Can you comprehend the mental model required? They were not just building a structure, they were drafting a continuous, physical graph of elevation in stone and concrete, all to serve the single variable of flow. This abstract mastery extended to their materials. The Roman arch was a standardized mathematical form, a predictable curve of proven strength that could be replicated anywhere, from a desert in Africa to a forest in Britain. Combined with their revolutionary concrete, a man-made stone that could be poured into any shape, they possessed a universal toolkit. An engineer arriving at a new river valley did not need to invent a new way to build. He simply applied the established abstract forms, the arch, the spec for concrete, the required gradient to the local stone and topography. The aqueduct was more than a water delivery system. It was a physical manifestation of a unified thought process, proving that a single, rigorous design philosophy could literally hold a civilization together. While Roman engineers were carving geometric certainty into the landscape, a parallel revolution in abstract thought was unfolding on the other side of the world. In ancient China, the engineering mind took a different yet equally brilliant path. Here, the great intellectual pursuit was not just about proving geometric truths, but about encoding logic itself into moving parts. This was the birth of algorithmic engineering, where machines were designed not merely to bear weight but to think. The south-pointing chariot is a stunning example. It was an ornate carriage topped with a figure that always pointed south, no matter which way the vehicle turned. How could this possibly work? Inside was not a magnet, but a complex arrangement of gears. When the chariot turned left, the gears would rotate to the right, perfectly compensating for the movement and keeping the figure locked in its southern orientation. This was not a simple machine, it was a physical computer. Its gear train performed a differential calculation, an abstract mathematical process that automatically adjusted for changing variables. It was a machine that could solve a problem in real time. This concept of mechanical computation reached its zenith with the astronomical clock tower of Song, built in the 11th century. This wooden tower, standing over 30 feet tall, was a cathedral of automated thought. Powered by a constant flow of water, its intricate system of gears and escapements did more than tell time. It modeled the cosmos. One part of the clock displayed the time of day, another showed the position of the sun and moon, while a rotating celestial globe mapped the stars. All of these movements were synchronized, driven by a single water wheel and a complex program encoded in its wooden gears. The machine was an algorithm made manifest. It took the predictable, cyclical patterns of the heavens and translated them into the precise, physical motion of its arms and spheres. Can you see the profound abstraction at work here? Song and his engineers were not building a monument to a single moment, like a pyramid aligned to a solstice sunrise. They were building a dynamic model, a machine that could run the calculations of the universe on its own forever. This represents a fundamentally different branch of abstract engineering, where Archimedes used formulas to predict an outcome for a human builder. The Chinese engineers built systems that executed the formulas themselves. Their machines embodied the logical process. They automated thought. This path of invention reveals a crucial truth about our journey from fire to formula. Abstract engineering was never a single, linear thread of progress. It was a vast and diverse tapestry of intellectual traditions, from the geometric proofs of Greece to the hydraulic networks of Rome to the algorithmic machines of China, all converging on the same magnificent goal: to master the physical world through the sheer power of the human mind. While the mechanical clocks of China marked the hours, a new intellectual empire was rising in the Middle East, one that would safeguard the flame of abstract knowledge through a dark age. The Islamic Golden Age did not merely preserve the engineering formulas of Greece and Rome, it built upon them with breathtaking originality. In cities like Baghdad and Damascus, scholars established the world's first organized engineering schools, transforming what was once a craft into a formal discipline based on geometry and proof. They became the indispensable librarians of the ancient world, translating and expanding upon texts that would have otherwise been lost forever. At the heart of this revolution was a man named Ismail al-Jazari. His life's work, the Book of Knowledge of Ingenious Mechanical Devices, was not just a catalogue of gadgets, it was a systematic encyclopedia of abstract mechanical principles. He detailed automata like his famous elephant clock, which used a complex water-driven system to mark the passing hours with moving figures and chiming sounds. But more important than any single machine was his methodology. Each device was presented with meticulous geometrical descriptions and precise instructions for its construction. Can you see the profound shift? This was engineering as a reproducible science, not a secret art. His book was a bridge connecting the theoretical proofs of Archimedes to the tangible, working machines of a new era. One of al-Jazari's most fundamental contributions was his mastery of the crank and connecting rod. This seemingly simple assembly is a cornerstone of modern machinery, and he was the first to document its use in a continuous, rotating machine. Think about the abstract conversion happening here. A crank turns circular motion, the motion of a water wheel or a hand-spun wheel, into the back and forth linear motion of a pump. This is a translation of energy forms, a physical realization of a mathematical relationship between rotation and reciprocal movement. It is the same principle that would one day power the pistons in a car engine, and it was being described with perfect clarity in the 13th century. The true power of this systematic approach is visible in the technical drawings that filled these Islamic manuscripts. For the first time, an engineer could convey a three-dimensional, complex machine on a two-dimensional page with enough precision that another engineer, working in a different city a century later, could build an improved version without ever seeing the original. This was the ultimate abstraction, the complete divorce of the engineering idea from its physical instantiation. The design lived on the page, a perfect blueprint that could be copied, shared, and perfected across a vast network of scholars. The Islamic Golden Age was the great crucible where ancient formulas were not just saved from extinction, but were alloyed with new discoveries, creating a body of systematic knowledge that would soon ignite the minds of the Renaissance. The systematic blueprints of the Islamic Golden Age migrated west, where they would be forged into stone and glass on an unimaginable scale. In the heart of medieval Europe, a new architectural language emerged, one that sought to build heaven on earth. The Gothic cathedral was more than a place of worship. It was a declaration that faith, guided by abstract geometry, could literally defy gravity. These structures reached for the sky with a skeletal lightness that seemed to ignore the very nature of stone. The secret to this miracle was not hidden within the walls, but braced against them from the outside. The flying buttress was a stroke of engineering genius, a stone arm that reached out from the cathedral's sides to catch the outward thrust of the massive roof vaults. It channeled these immense forces down and away from the fragile walls, turning the building's own weight against itself. This externalized support system was a radical rethinking of structure. The wall was no longer a load-bearing cliff, but a delicate screen that could be filled with vast, colorful narratives of stained glass, flooding the interior with divine light. How did master masons design such intricate stone skeletons without modern mathematics? They worked out their complex three-dimensional puzzles on tracing floors, large flat surfaces of plaster or stone where they would scratch out full-scale diagrams of arches, windows, and vaults. These were their geometric blueprints, abstract lines scratched in plaster that would later be translated into the soaring ribs of a stone ceiling. Can you picture the process? A team of craftsmen looking down at a giant geometric proof on the floor, then looking up to see that same logic realized 100 feet in the air. The construction of a single cathedral was an act of profound abstract faith that spanned generations. A master mason would lay the foundations for a structure he knew he would never see completed. He was working for a future he could only imagine, trusting that his successors would faithfully execute the geometric principles he had established decades or even a century earlier. This required a shared, enduring vision, a collective belief in an abstract plan that far outlived any single human life. The cathedral was a physical dialogue between the dead, the living, and the unborn, all collaborating on a single, monumental prayer built from faith and formula. It was the ultimate expression of abstract engineering, giving tangible, breathtaking form to the most intangible of human experiences, the yearning for the divine. The soaring stone of the cathedral was a testament to faith, but the Renaissance draftsman sought to capture a different kind of truth on paper. In the quiet of his studio, Leonardo da Vinci's pen was not merely sketching machines, it was dissecting the invisible forces that governed the world. His codices are a wilderness of invention, filled with helicopters that could not yet fly, tanks that could not yet roll, and bridges that spanned impossible distances. These were not flights of fancy, they were rigorous explorations of abstract principles like aerodynamics and structural stress, all worked out in the two-dimensional realm of ink and paper. How could a man design a working parachute centuries before the first human would leap from a great height? He was not building the object itself, he was engineering the underlying idea of air resistance, giving it form and function in a drawing long before it could be tested in the physical world. This new power was fueled by a crucial artistic development, the mastery of perspective. For the first time, an engineer could represent a complex, three-dimensional object with geometric accuracy on a flat surface. This was more than a realistic picture, it was a predictive model. By drawing a machine from multiple angles and in cross-section, Leonardo could analyze how its parts would interact, where stress would concentrate, and how motion would transfer from one gear to another. He could see the machine's logic and its potential flaws before a single piece of wood was ever carved. These drawings were his laboratory, a page filled with successive iterations of a water wheel or a siege engine was a visual record of a thought experiment in progress. Each line was a question, each shading an hypothesis about weight, force, and material. The pencil and ruler became his most vital tools, allowing him to wage the first and most important battle of any engineering endeavor, the battle of ideas. He proved that the most profound engineering happens not in the workshop, but in the mind and on the page, where the abstract blueprint is the true birthplace of reality. Leonardo's sketches were brilliant possibilities, but they still lacked the predictive power of a universal law. The world remained a collection of individual puzzles until the 17th century, when a new breed of thinkers declared that the entire cosmos could be understood through numbers. The scientific revolution did not just offer new tools, it offered a new reality, one governed by elegant mathematical formulas that applied equally to an apple falling from a tree and the moon circling the Earth. At the heart of this revolution was Isaac Newton, whose laws of motion provided a complete mathematical framework for force and movement. His first law introduced the concept of inertia, the simple yet profound idea that an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by an external force. This was a radical departure from the ancient belief that objects naturally sought rest. It meant that motion itself was a state, not a process of decay. His second law gave engineers their most crucial equation: force equals mass times acceleration. For For the first time, you could calculate exactly how much push was needed to move a specific weight a certain distance in a given time. And his third law, for every action there is an equal and opposite reaction, explained everything from the recoil of a cannon to the fundamental principle of rocket propulsion. But Newton's grandest abstraction was the law of universal gravitation. He proposed that every single particle in the universe attracts every other particle with a force that can be precisely calculated. This was the ultimate act of abstract engineering, a single mathematical rule that bound the cosmos together, from the orbit of planets to the tide of the oceans. How could one even begin to work with such powerful, all-encompassing ideas? The answer emerged simultaneously in the minds of Newton and the German philosopher Gottfried Wilhelm Leibniz, a new form of mathematics called calculus. While algebra dealt with static quantities, calculus was the mathematics of change. It provided the language to describe continuous motion, to calculate the exact speed of a falling object at any given instant, or to find the area under a complex curve representing a force over time. This was the essential toolkit for turning Newton's physical laws into practical engineering. You could now model the stress on a bending bridge beam, the flow of water through a pipe, or the acceleration of a piston in an engine, all on paper. This era cemented a breathtaking new faith for engineers, the belief that the universe was not a mysterious and capricious place, but a rational system operating on a set of decipherable formulas. Engineering was no longer just an art or a craft. It was now the disciplined application of those universal formulas to human needs. The abstract blueprint had evolved into a predictive mathematical model, and the world was now a system waiting to be calculated. Isaac Newton gave engineers the mathematical laws of the cosmos, but the first machine to truly master those laws ran on steam and soot. Inside a Newcomen engine, a great iron beam rocked slowly back and forth, its rhythm driven by a hidden dance of pressure and vacuum. The process was simple in action but profound in its abstract demands. A piston sat inside a cylinder filled with steam. Then, a jet of cold water was injected, condensing that steam in an instant. The sudden disappearance of the vapor created a partial vacuum, and the relentless pressure of the outside atmosphere slammed the piston downward with immense force. This was the conceptual leap, the harnessing of an invisible force, the vacuum, to generate motion. These early engineers were manipulating a ghost, a nothingness that could do real work. They were taming the abstract relationship between heat, pressure, and volume long before the science of thermodynamics had a name. James Watt's legendary improvement did not come from a new material or a stronger metal, but from a clearer thought. Watching a Newcomen engine at work, he was struck by its inefficiency. The entire cylinder had to be heated to fill it with steam, and then cooled to condense it over and over, wasting a colossal amount of fuel and time. His brilliant insight was to separate these two conflicting processes. The separate condenser was a piece of abstract reasoning made of brass. Watt kept the main cylinder perpetually hot, but he piped the used steam into a separate, always cool chamber to be condensed. This single idea, based on a mental model of heat as a precious quantity to be conserved, dramatically doubled the engine's efficiency. He was not just fixing a machine, he was optimizing an invisible energy flow. But how do you improve what you cannot see? The answer was sketched onto a piece of paper. The indicator diagram was a revolutionary tool, a graph that plotted the pressure inside the cylinder against the volume of steam. As the engine ran, a stylus would trace a looping line on the chart. That closed loop was the engine's soul made visible. Engineers could now see the inefficiencies, the points of pressure loss, the energy wasted as heat. The diagram transformed the steam engine from a clanking metal beast into an abstract mathematical problem that could be analyzed, tweaked, and perfected on a desk. This was the final piece of the puzzle. The steam engine did not just power looms and locomotives, it powered a new way of thinking. It was the mother of the Industrial Revolution precisely because it was the ultimate expression of applied thermodynamic abstraction, a machine built from a deep understanding of invisible laws, turning theoretical principles into relentless, world-changing motion. The relentless rhythm of the steam engine demanded a new world, one where distance and duration were no longer dictated by nature. To lay a railway across a continent was to wage war on geography itself, an abstract battle fought with trigonometry and contour line. Before a single mile of track could be laid, surveyors had to draft the land into submission. Their maps were not mere pictures of hills and rivers, but complex topographical renderings, converting the chaotic rise and fall of the Earth into a system of precise elevation lines and calculated gradients. Can you envision the mental leap required to look at a rugged mountain pass and see, on a flat sheet of paper, the exact path for a gentle, train-friendly slope? This was engineering on a colossal scale, where the abstract idea of a route existed long before the physical reality of the track, a line drawn through the wilderness based entirely on mathematical possibility. This conquest of space was matched by a revolution in time. Before the railways, the sun ruled the day. Noon was simply when the sun reached its highest point in your particular town. But a train traveling from, say, New York to Chicago would pass through dozens of these local times, making a coherent schedule impossible. The solution was an act of pure abstraction, the imposition of standardized time zones. The continuous, flowing nature of the day was carved into 24 rigid, identical slices, creating an artificial grid of time that blanketed entire regions. The clock on the station wall no longer reflected the local sky. It reflected a man-made system, a shared temporal fiction that every train and every traveler had to agree upon for the network to function. This new, synchronized world demanded a nervous system. As traffic intensified, the simple act of moving trains safely became a problem of logic. How do you prevent two trains heading in opposite directions from meeting on a single track? The answer was the development of complex signaling protocols. Each signal was not just a colored light, it was a piece of a distributed intelligence, a physical manifestation of an abstract rule governing the occupation of a block of space. Elaborate switching systems in rail yards were like mechanical computers, their interlocking levers ensuring that a route could not be set that would lead to a collision. The entire railway was a vast, living machine, its operation dependent on a web of abstract concepts, from the mapped gradient of a hill to the scheduled minute of departure to the logical state of a signal. It was not just transporting people and goods, it was engineering the very fabric of reality, training humanity to think in terms of systems, schedules, and synchronized clocks. The railways had woven a mechanical logic across the land, but the next great network would be built from something entirely invisible. Electrification demanded that engineers design a continent-wide system for a force they could never see, a river of energy that flowed silently through copper wires. This challenge ignited one of history's most dramatic engineering battles, a war of currents fought between two brilliant minds with opposing visions. On one side stood Thomas Edison, championing direct current. His system was simple and intuitive, like a river flowing steadily in one direction. It worked beautifully over short distances, lighting up the labs and streets of Manhattan. But this very simplicity was its fatal flaw. Direct current could not travel far without losing its strength, demanding a power station on every city block. The future needed to flow across states, not just streets. Nikola Tesla, armed with the abstract power of mathematical formulas, offered a radical alternative: alternating current. Instead of a steady flow, his current pulsed back and forth, rapidly changing direction. This seemed chaotic, even dangerous, but it held a magical property. Using a transformer, an engineer could effortlessly change its voltage, the electrical pressure that pushes the current along. This was the key abstraction. To send power over vast distances, you could use a transformer to step the voltage up to an incredibly high pressure. At such immense voltages, the current, and thus the energy lost as heat due to the wire's resistance, became negligible. Then, at the far end of the line, another transformer would step the voltage back down to a safe level for homes and factories. How do you even begin to calculate such a system? The essential tool was a simple, powerful formula known as Ohm's law. It states that the current in a circuit is equal to the voltage divided by the resistance. For engineers designing a power line, this equation was their compass. It allowed them to predict exactly how much energy would be lost as heat over 100 miles of cable, and to calculate the perfect wire thickness and voltage to maximize efficiency. They were not just laying copper, they were solving a continent-wide mathematical puzzle where the variables were pressure, flow, and friction. The grid that emerged from this conflict is a masterpiece of systems engineering, a living abstraction that must remain in a state of perfect, instantaneous balance. Electricity cannot be stored in large quantities. It must be generated at the exact moment it is consumed. When you flip a light switch, a power plant hundreds of miles away must instantly respond to that new demand, increasing its output by a minuscule amount to keep the entire system's frequency stable. This requires a real-time, abstract model of the entire network, a constantly updated calculation of generation and load that functions as the grid's beating heart. Taming this invisible force was the ultimate act of abstract engineering, building a world powered by a phenomenon whose behavior was only truly understood through the elegant language of mathematics. The grid tamed an invisible river of electrons, but a far more turbulent medium awaited its master. For centuries, the dream of flight was shackled to the shape of a bird's wing, a path of imitation that led to countless failures. The sky would not be conquered by building better gliders alone, but by decoding the abstract language of the air itself. The pivotal breakthrough occurred not in a workshop, but in a 6-foot-long wooden box. The Wright brothers' wind tunnel was a laboratory for pure abstraction, a place where the chaotic, invisible forces of wind were forced to reveal their secrets. Inside this simple apparatus, they tested hundreds of miniature wing shapes, methodically recording how each one interacted with the moving air. They were not building a machine, they were building a database, transforming the art of flight into a series of quantifiable, repeatable experiments. From this painstaking data emerged the essential formula for lift. This equation showed that the upward force on a wing was not a mystery, but a predictable result of several variables: the shape of the wing, the speed of the air moving over it, and the density of the air itself. A curved wing, or airfoil, forces air to travel faster over its top surface than its bottom, creating a region of lower pressure above the wing. It is this pressure difference, described by the abstract principle of Bernoulli's equation, that generates lift. Can you see the profound shift? Flight was no longer about crafting the perfect feathery shape. It was about solving a mathematical problem. The design of an airplane became a continuous exercise in balancing 4 competing abstract forces, each governed by its own set of relationships. Lift must counteract weight, the relentless pull of gravity. Thrust from the propeller must overcome drag, the invisible friction of the air itself. The pilot in the cockpit is not just steering a machine, They are conducting a symphony of physics, constantly adjusting controls to maintain an equilibrium described by formulas. The Wright Flyer that lifted from the sands of Kitty Hawk was a physical manifestation of these calculated abstractions. Its wings were not copies of nature, but carefully designed surfaces whose performance had been predicted on paper. Its propeller was not an oar for the air, but a rotating airfoil engineered using the same lift equations. Their breakthrough was the ultimate proof that to conquer a physical frontier, you must first master its abstract blueprint. The sky was not one with wood and wire, but with data, equations, and the quiet, systematic power of the human mind. The sky was conquered by understanding the invisible flow of air, but the modern cityscape was built by learning to design the very ground it stands upon. We engineered a new kind of stone. This was the concrete revolution, a triumph of abstract materials science that gave us a rock with predictable, programmable properties. Its story begins not in a modern laboratory, but in the shadow of Mount Vesuvius, where Roman engineers discovered a volcanic ash called pozzolana. When mixed with lime and water, this powder underwent a mysterious chemical transformation. Instead of simply drying, it reacted with water in a process called hydration, forming a crystalline glue that bound sand and gravel into a monolithic, water-resistant stone. This was the first concrete, and its creation was an act of pure chemical abstraction, turning a pile of inert dust into a living, hardening material through a reaction the Romans could not see, only harness. For centuries, this knowledge was lost, only to be rediscovered and refined in the 19th century with the invention of Portland cement. This was not a natural material, but a precisely manufactured powder, baked in a kiln from a calculated recipe of limestone and clay. The process demanded a deep understanding of the abstract relationships between temperature, chemical composition, and the final product's strength. The formula for a concrete mix itself is a sophisticated abstraction. It is not a single recipe, but a family of recipes, each balancing precise ratios of cement, water, and aggregates to achieve specific goals like high early strength, resistance to freezing, or exceptional fluidity for pouring into complex molds. This transforms the chaotic variability of natural sand, rock, and water into a uniform, predictable, and engineered substance. Yet concrete, for all its compressive strength, has a critical weakness. It is brittle and fails easily under tension, the stretching and pulling forces present in a beam or a floor slab. The conceptual leap that changed everything was the idea of embedding a skeleton of steel rebar within the wet concrete. This was an abstract marriage of two materials, each compensating for the other's fundamental flaw. The concrete protects the steel from corrosion and fire, while the steel absorbs all the tensile stresses, the forces that would cause plain concrete to crack and fail. This combination, reinforced concrete, created a composite material with designed, hybrid properties that did not exist in nature. It allowed engineers to design for complex load distributions and bending moments, to create structures that could cantilever over empty space and soar to incredible heights. The very essence of a skyscraper or a vast, sweeping bridge is this abstract partnership, a silent dialogue between the compressive strength of synthetic stone and the tensile resilience of forged iron, a collaboration engineered not by chance but by formula. The silent logic of the concrete skyscraper found its echo in the rhythmic clatter of electromechanical relays. Deep within the telephone exchanges and factory control rooms of the early 20th century, a new kind of machine was being born, one that manipulated not physical force but pure information. Engineers were discovering they could build abstract reasoning out of brass, wire, and switches. The humble relay was the key, a simple device where an electrical current would flow through a coil of wire, creating a magnetic field that physically pulled a metal switch from one position to another. This was a binary thought made real. The switch was either open or closed, the circuit was either broken or complete. In this simple on-off state, engineers found a way to represent the most fundamental concepts of logic, the true and false of Boolean algebra. A closed circuit could mean true, an open circuit could mean false. By wiring these relays together in specific patterns, they could create circuits that performed logical operations. One arrangement of relays could function as an AND gate, where the output would only be true, the circuit only closed if two input switches were both closed. Another configuration could create an OR gate, where the output was true if either one input or the other was active. This was the conceptual leap that fused the abstract and the physical. A machine could now make a logical decision. The person who formalized this marriage was a young student named Claude Shannon. In his groundbreaking master's thesis in 1937, he demonstrated with elegant clarity that the complex rules of Boolean algebra, a branch of mathematics dealing with truth values, mapped perfectly onto the behavior of electrical switching circuits. He proved that you could design a circuit to solve any logical problem you could state in algebraic terms. You were no longer just building a machine to calculate, you were building a machine to think. The ultimate expression of this principle was the Harvard Mark I, a colossal machine 50 feet long and 8 feet high. Its interior was a mesmerizing forest of spinning shafts, clicking relays, and whirring gears. But for all its physical grandeur, its true genius was abstract. The machine was programmed using paper tape with holes punched in it, a sequence of instructions where a hole meant 1 and no hole meant 0. The Mark I could not think for itself, but it could execute a long, complex series of logical and arithmetic steps automatically. It broke down a massive calculation, like computing artillery firing tables, into thousands of tiny, simple decisions, each one a single click of a relay. The relentless, automated execution of these binary choices produced a result far beyond human speed. In that room of rhythmic noise, a profound new idea was taking physical form, the realization that thought itself, or at least the mechanical process of logical deduction, was something that could be engineered. The rhythmic clatter of the Mark I's relays was a symphony of physical logic, but its scale was its limitation. The next great leap in abstraction demanded that we move from a room-sized machine of moving parts to a universe of logic etched onto a sliver of stone. The invention of the transistor shattered the old paradigm, replacing the mechanical relay with a tiny switch made from a semiconducting material like silicon. This was not just a smaller component, it was a fundamental shift. The transistor had no moving parts. It controlled the flow of electricity using nothing but the application of a smaller electrical signal itself. The abstract machine was being liberated from the world of physical motion. This miniaturization exploded with the integrated circuit, where engineers learned to carve not one, but thousands, then millions of these tiny switches onto a single piece of silicon. The surface of a microchip is a city of logic, a meticulously planned metropolis of microscopic towers and canyons made of metal and doped silicon. But how do you possibly design such an impossibly complex city? The answer was to build it first in the abstract realm of symbols. Engineers stopped thinking about individual transistors and started thinking in terms of logic gates, the same and or, and not functions that once required clunky relays. These gates became the new alphabet, the basic building blocks for constructing any computational thought. On a computer screen, an engineer would assemble these symbolic gates into a schematic, a pure abstract diagram of the chip's intended function. This diagram was a blueprint for behavior, not for physical form. It described what the chip should do, not what it would look like. The miraculous step was translating this abstract diagram into a physical object. This is achieved through photolithography, a process that feels like alchemy. The circuit design is turned into a series of immense masks like photographic negatives. These masks are then used to project patterns of ultraviolet light onto a silicon wafer coated with a light-sensitive chemical. Where the light strikes, it hardens the coating, creating a stencil. Subsequent chemical baths then etch away the unprotected areas, carving the canyons and depositing the metals that form the transistors and their interconnections. Can you grasp the profound abstraction at work here? A logical idea, a diagram of thought, is written onto a chip using nothing but patterns of light. It is a form of writing where the ink is photons and the parchment is a crystal of silicon. This process became so complex that engineers developed specialized languages, known as hardware description languages. With these, they no longer even needed to draw the gates. They could write code that described the chip's behavior in text, just like a software program. A single line of this code could represent the function of 10,000 transistors. Powerful computer simulators would then run this abstract description, testing the virtual chip's logic with millions of simulated inputs to ensure it would work perfectly before a single, incredibly expensive physical prototype was ever produced. The microchip you hold in your hand is the ultimate expression of this journey. It is a physical object, a piece of sand, whose entire purpose and function are dictated by an invisible, abstract logic designed into its very atomic structure. It is a mountain of thought condensed into a speck of stone. The microchip gave us a universe of logic etched in silicon, but that universe remained silent until we taught it to speak. Software engineering is the art of building castles in the sky, constructing entire, functional worlds from nothing but the pure abstractions of logic and language. The first programmers communicated with the machine in its own native tongue, machine code, a brutal sequence of ones and zeros that represented the most direct commands to the hardware. Each instruction was a single, painstaking step, like telling a friend how to walk by individually commanding every muscle fiber in their leg. This was engineering at the absolute ground level, a conversation in binary that left no room for error. The first great abstraction was the development of assembly language, which replaced the cryptic numeric codes with simple, human-readable mnemonics. An instruction to add two numbers was no longer a string of binary digits, but the word add. This was a monumental shift, the first layer of translation between human intent and machine execution. But the true revolution came with high-level programming languages like Fortran and COBOL. These languages allowed engineers to stop thinking about the machine's internal wiring and start thinking about the problem they wanted to solve. They could express complex mathematical formulas or business logic in a syntax that looked almost like a condensed form of English or algebra. The computer itself would then use a special program called a compiler to translate these high-level commands back down into the machine code it understood. This was the ultimate delegation of drudgery, freeing the human mind to work at a higher plane of thought. With this new power, engineers began to develop sophisticated paradigms for organizing this abstract construction. Object-oriented programming, for instance, allows a programmer to model a real-world entity, like a bank account or a car, as a self-contained software object. This object bundles together its data, its account balance or current speed with its behaviors, the methods for making a deposit or applying the brakes. This is a profound act of abstract modeling, creating a digital twin of a real-world system where interactions between objects mimic the interactions in the physical world. The entire process of creating software, from gathering user requirements to designing the overall system architecture, is a continuous exercise in managing abstraction. A software architect does not draw plans for physical walls and wires, but for layers of logic and data flow. They design the blueprints for intricate, invisible cathedrals of code, defining how thousands of individual modules will interact to perform a single, seamless function. Every program you use, from a simple word processor to a complex video game, is one of these castles. It has no physical substance, no weight or color. It exists only as a precise, orchestrated pattern of electrons dancing within a circuit, a ghostly machine built entirely from human thought. Software is the ultimate proof that our most powerful engineering no longer happens in the world of atoms, but in the boundless realm of pure idea. The vacuum of space is the ultimate test of abstract thought. Here, nothing is familiar, and a single engineering flaw means instant, catastrophic failure. The Apollo program to land a human on the moon was not just a project of rockets and metal. It was a monumental exercise in managing 1 million invisible variables. Every step of the 250,000-mile journey was governed by the cold, precise laws of orbital mechanics. Engineers could not build a prototype of the mission. They had to build a perfect mathematical model of it. They abstracted the entire voyage into a series of complex calculations, predicting the exact thrust needed to break free of Earth's gravity, the delicate ballet of docking in lunar orbit, and the precise angle for a safe re-entry into the atmosphere. Each maneuver was a problem in physics, solved on paper long before a spacecraft ever left the launch pad. How do you ensure survival in a realm where every known support system is absent? The answer was an abstract principle called redundancy. For any component critical to life, the engineers designed not one, but 2 or 3 independent backups. If a primary system failed, a duplicate would instantly take over. This was not merely adding spare parts, it was embedding a philosophy of resilience into the very blueprint of the spacecraft, a formal acknowledgement that in an untested environment, the unknown was the greatest enemy. To prepare for this hostile void, NASA created its own artificial reality here on Earth. The simulators were masterpieces of abstraction, complex machines that replicated the spacecraft's cockpit and its functions. Astronauts spent countless hours in these boxes, practicing every normal procedure and rehearsing every conceivable emergency. They were not just learning switches, they were internalizing a dynamic model of the mission, training their minds and bodies to respond to scenarios that had only ever existed as data and probability. The successful landing on the lunar surface was the ultimate validation of this approach. It proved that humanity could engineer a successful outcome for an environment it could not fully experience, by building flawless abstract models of that environment first. We reached the moon not because we built a powerful rocket, but because we learned to think in its language, the language of physics, probability, and profound foresight. The moon landing was a triumph of centralized, meticulous planning, but the next great network would thrive on the very opposite principle. It was designed not for a single mission, but for 1 million unknown ones, a system built to survive its own partial destruction. The Internet is a ghost in the machine, a global nervous system engineered from pure logic rather than a master blueprint. Its foundation rests on a simple, brilliant abstraction, the idea of breaking every piece of information into tiny, standardized envelopes called packets. Think of sending a long letter not in one envelope, but by writing each sentence on a separate postcard. You mail all the postcards at once, and they may each take a completely different route across the country. Some might travel by truck, others by plane, a few might even take a scenic, slower path. When they all finally arrive at their destination, they are reassembled into the original message. This is packet switching, a radical departure from the old telephone system that required a dedicated physical circuit to be connected from caller to receiver for the entire conversation. The internet needs no permanent road. It is a dynamic map where every packet finds its own way in the moment, flowing around congestion or damage like water finding cracks in a wall. Guiding these digital postcards are the unseen rules of the road, the protocols known as Transmission Control Protocol and Internet Protocol, or TCP/IP. IP is the universal addressing system, giving every device on the network a unique number, its IP address. This is how a packet knows where it is ultimately headed. TCP is the reliable postmaster. It breaks your data into packets, numbers them, and then, at the other end, checks that they all arrived. If a packet is lost or damaged, TCP simply asks for it to be sent again. This elegant handshake between two abstract rules allows a smartwatch in Tokyo to communicate flawlessly with a server in Texas, without either one needing to know anything about the tangled web of cables and routers in between. On top of this resilient data highway, another layer of abstraction was built, one that gave the internet its human face. The World Wide Web introduced a universal language for information itself. HTML is the set of instructions that tells your browser how to display a page, turning abstract code into headlines, paragraphs, and images. HTTP is the simple command language that your browser uses to ask a faraway computer for a specific page. And the URL is the elegant abstraction we all use every day, a simple, memorable address that masks a complex IP address and file path. When you type a web address, you are speaking a spell that summons a world of information from a server you will never see. The internet is therefore a universe of pure information, a physical infrastructure of fiber optic cables and data centers whose sole purpose is to serve an abstract, borderless world of data, connection, and shared knowledge. It is the most complex thing humanity has ever built, precisely because its true architecture is not made of steel or silicon, but of agreements, protocols, and the relentless, invisible flow of thought. The ghostly architecture of the internet now finds its ultimate challenge in the wet, intricate machinery of the human body. In recent decades, engineering has turned inward, applying its abstract principles to the most complex system ever encountered, life itself. This is biomedical engineering, a field that treats the heart not just as a pump, but as a problem in fluid dynamics, and the brain not just as a mind, but as a network of electrochemical signals. The first step is always to build a model, a mathematical abstraction that simulates a physiological process. To design an artificial heart valve, engineers do not start with metal and plastic. They start with equations, creating a digital simulation of how blood flows, swirls, and exerts pressure. This virtual model allows them to predict where dangerous clots might form or where tissue might tear, refining the design in the abstract realm long before it is ever tested in a living being. This same abstract reasoning is embedded in the artificial knee or hip joint. Its development is a triumph of material science, requiring an understanding of how to replicate the unique properties of bone and cartilage. Bone is not just hard, it is a living composite that is rigid yet slightly flexible. Cartilage is a near-frictionless surface that self-lubricates. The engineering challenge is to abstract these biological functions into synthetic materials, creating alloys and polymers that can withstand millions of cycles of loading and unloading, while seamlessly integrating with the body's own tissues. How do you see inside this living machine without cutting it open? The magnetic resonance imaging scanner provides the answer through a breathtaking application of abstract physics. An MRI machine does not take a picture. It listens to the faint magnetic songs of the atoms within your body. The process relies on nuclear magnetic resonance, a quantum mechanical phenomenon where the nuclei of hydrogen atoms, abundant in water and fat, act like tiny magnets. The machine first surrounds the body with an immensely powerful, perfectly uniform magnetic field, forcing these billions of atomic magnets to align. Then it pulses the body with a specific radio frequency, just the right energy to knock these tiny magnets out of alignment. When the pulse stops, the atoms snap back into place, and as they do, they each release a unique radio signal of their own. The machine's computer listens to this chorus of returning signals and, using a mathematical process called a Fourier transform, decodes it into a detailed, three-dimensional map of our inner landscape. This is abstract engineering at its most profound, turning the esoteric behavior of subatomic particles into a clear window for healing. This conceptual journey reaches its logical extreme with synthetic biology, where the very components of life are abstracted into standardized parts. DNA sequences that perform specific functions are cataloged as biobricks, like a registry of biological Lego pieces. An engineer can now design a new biological circuit by assembling these abstracted parts on a computer screen, perhaps programming a bacterium to produce a life-saving drug or to detect an environmental toxin. We are no longer just repairing the body's machinery. We are beginning to redesign it from the ground up, using the same principles of abstraction that took us from fire to formula. The line between the evolved organism and the engineered system is blurring, all guided by our relentless drive to model, understand, and ultimately command the processes of life itself. The human engineer is no longer the sole author of the design. We have reached a point in our story where the formulas we created are beginning to create themselves. This is the algorithmic age, a new chapter defined by generative design. Here, an engineer does not draw a bridge support or an airplane bracket. Instead, they speak to the machine in the language of abstract goals and constraints. They define the problem, the required strength, the maximum weight, the available materials, and the forces that will act upon the final part. Then they set the algorithm loose. The artificial intelligence does not iterate on a human idea. It explores the entire universe of physical possibility. It spawns thousands, even millions, of radical design options, each one a unique solution to the abstract puzzle. The results often look alien, like bones grown by nature or the intricate lattice of a coral reef. These are forms a human mind would likely never conceive, yet they are perfectly, mathematically optimized to bear the specified load with the absolute minimum material. This is abstract engineering performed at a scale and speed beyond human cognition. The same principle is revolutionizing materials science. Machine learning models are now trained on immense databases of molecular structures and their resulting properties. By finding deep, hidden patterns within this data, the AI can predict the behavior of entirely new material combinations that have never been synthesized. It can suggest a new alloy that is both lighter and stronger, or a polymer with a specific flexibility and heat resistance, all through a form of statistical reasoning performed in silicon. Perhaps the most profound expression of this meta-evolution is happening in the very place our digital world is born, inside the microchip. The design of a modern processor involves many billions of transistors. No single human or even a vast team can possibly track the astronomical complexity of their interconnections. This is where electronic design automation, or EDA, comes in. Artificial intelligence is now used to arrange these microscopic components, to route the nanoscale wires between them, and to verify that the final, monstrously complex design will function as intended. We are engineering circuits of such profound intricacy that they, in some aspects, surpass our own capacity to fully comprehend them. The engineer's role is undergoing a fundamental shift. We are moving from crafting the final formula to crafting the intelligent process that discovers the formula. We are building the abstract machine that builds the machine. This is not the end of the journey from fire to formula, but a breathtaking new beginning where the flame of human creativity ignites a self-sustaining forge of digital invention. Our civilization now faces a test that demands a new kind of abstraction, one that encompasses the entire planet. The challenge of sustainability forces us to engineer not just objects, but the very flows of energy and matter that sustain our world. To do this, we must first build a perfect digital twin of the Earth itself. Vast computational climate models are these twins, staggering abstractions that attempt to simulate the chaotic dance of our global atmosphere and oceans. They are not simple forecasts, but intricate webs of mathematical formulas representing sunlight, cloud cover, ocean currents, and the carbon cycle. These models run on the world's most powerful supercomputers, processing petabytes of data to answer the most critical engineering question of our time: what happens next? They allow us to see the abstract consequences of our actions, projecting the long-term impact of rising greenhouse gases on global temperatures, sea levels, and weather patterns. This planetary-scale simulation is the essential blueprint for our survival. Applying this abstract knowledge requires re-engineering the backbone of our civilization, the power grid. The old model of a few massive power plants is giving way to a dynamic, intelligent network known as the smart grid. Think of it as the internet for electricity. Its genius lies in its ability to abstractly balance supply and demand in real time, a monumental task when integrating volatile sources like solar and wind. When the sun stops shining or the wind dies down, the grid must instantly compensate by drawing power from batteries or other sources. Conversely, when renewable generation surges, it must intelligently route that power to where it is needed or store it for later. This is managed through a constant, invisible conversation between smart meters in homes, sensors on power lines, and control centers running complex algorithms. The grid is no longer a one-way street, but a responsive, thinking organism, an abstraction of energy flow made intelligent. This new logic extends to the things we make and use. The circular economy is perhaps the ultimate abstract engineering model for our material world. It redefines the entire life cycle of a product, designing waste and pollution out of existence from the very beginning. In a linear economy, we take, make, and dispose. In a circular one, we design for disassembly, reuse, and regeneration. An engineer creating a smartphone for a circular model does not just design its function, they design its future. They must abstract its entire journey, specifying how every component, from the rare earth metals in the screen to the lithium in the battery, can be easily recovered and fed back into the manufacturing process as a technical nutrient. This shifts the fundamental goal from creating a product to maintaining a perpetual flow of valuable materials. It turns our entire industrial system into a loop that we must consciously engineer, an abstract circuit where nothing is truly thrown away. We are learning to engineer the metabolism of our civilization itself, using global-scale abstractions to ensure that our footprint on the planet is not a scar, but a sustainable, regenerative pattern. The principles that built our world now dissolve into a shimmer of probabilities at the quantum frontier. Here, engineering confronts a reality where a single particle can be in two places at once, and an object's properties remain undecided until the very moment they are measured. This is the domain of quantum mechanics, and harnessing its bizarre rules is the next great act of abstract engineering. To build here, we must first abandon all our classical intuitions. The fundamental unit of this new world is not the simple binary bit, a 0 or a 1, but the quantum bit or qubit. A qubit can exist as a 0, a 1, or, in its most powerful state, a superposition of both 0 and 1 simultaneously. Think of it not as a simple switch, but as a spinning coin, hovering in a state that is both heads and tails at the same time. This single, abstract property unlocks a computational power that grows exponentially with each new qubit added to the system. But this power is incredibly fragile. The quantum state of superposition is a whisper of a thought, easily shattered by the slightest interaction with the outside world, a phenomenon known as decoherence. The primary task of a quantum engineer, then, is not just to build a computer, but to build a fortress of silence around these delicate qubits. This involves engineering some of the coldest places in the known universe, chilling processors to within a fraction of a degree above absolute zero, and shielding them from all stray magnetic fields and vibrations. The machine itself is a monument to abstracting quantum weirdness into stable hardware. An even more profound resource is quantum entanglement, a ghostly connection where two qubits become inextricably linked. Measuring the state of one instantly defines the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, is not magic. It is a physical phenomenon that engineers are learning to orchestrate. They use entanglement to create deeply correlated qubits that can work in concert, performing complex calculations through a form of quantum interference, where probability waves cancel each other out or reinforce each other to arrive at an answer. The entire process of programming such a machine is itself an exercise in advanced abstraction. You are not writing a list of commands, but designing a choreography of quantum states, guiding their probabilities to evolve in such a way that the correct solution emerges with the highest likelihood. This is engineering at the very boundary of reality, using formulas that describe a world of inherent uncertainty to create devices of unimaginable precision. The promise is a new class of machines that could design life-saving drugs by simulating molecular interactions atom by atom, or break current encryption by factoring astronomically large numbers in seconds. We are learning to build with the fabric of possibility itself, turning the most counterintuitive rules of the universe into the foundation of our next technological revolution. Our long journey from fire to formula shows us something fundamental about ourselves. It is not merely a chronicle of tools and machines, but the epic story of the human mind learning to make its inner world real. We began by taming a single, tangible flame, and we have arrived at a point where we write mathematical spells that command the behavior of ghostly quantum particles. Every step of this path has been a leap further into the realm of pure idea, a greater mastery over the abstract. The enduring mystery of Stonehenge or the Great Pyramid is not just the immense physical labor, but the profound mental leap that preceded it. How did someone, for the first time, conceive of a right angle or visualize the precise arc of the sun throughout the year, and then have the audacity to encode that vision into millions of tons of stone? The true engine of our progress has never been brute strength, but this breathtaking capacity for abstraction. It is the ability to look at a fallen log and see the principle of the lever, to stare at a blank sheet of paper and see the soaring arches of a cathedral, to draft a simple protocol and see the entire interconnected world of the internet. Now we stand at a new precipice where artificial intelligence designs worlds beyond our imagination and quantum physics redefines the nature of reality.